Okay, welcome back, guys. We're going to look at section 3.3 today, and this is on what is referred to in this textbook as the addition rule. Okay, so in the previous section, guys, we looked at finding the probability that two events would both occur. Okay, so we found what's referred to in math as the intersection, the probability of the intersection of those two events. So now we're going to look at determining the probability of what's referred to as the union of two events. So what that means is the probability that event A occurs or event B occurs. So the difference there is the conjunction A and B versus A or B. Okay, so last class we looked at determining the probability that A and B both occur. So now we're going to look at the it's referred to as the union, although I don't think that this book actually uses that terminology. But anyway, first thing we'll look at is determining whether two events are what is referred to as mutually exclusive. Okay, and then also how to use the addition rule to find the probability of two events. Okay, so let's first talk about this idea of mutual exclusivity. So two events, A and B, are going to be said to be mutually exclusive if they cannot both occur. Okay? In other words, A and B have no outcomes in common. Okay, and what I've got down here is these are both what are referred to as Venn diagrams. Okay, so they're a visual way or a convenient way for us to visualize kind of what's going on when we start talking about the probability of events. So if this square right here, guys, represents the sample space, okay, it's a set, it's the set of all possible outcomes, and event A is right here, it's comprised of the outcomes in this area, and then event B is right here, it's comprised of the outcomes in this other area. You notice these two circles do not overlap. So this visually shows us that these two events are mutually exclusive. Here's an example in which the two events are not mutually exclusive. So you can see that there is actually an intersection. So what this means is that there are outcomes in both events. Okay. All right, so in other words, both events could actually occur together, and that's not the case when two events are mutually exclusive. All right, so let's look at an example, or some examples rather. So the first thing we want to do is determine if two events are in fact mutually exclusive. Okay, so number one, event A is going to be, okay, so we're talking about a coin toss. Event A is that the coin lands on heads, and then event B is that the coin lands on tails. Well, these two events are mutually exclusive, guys, because you know if you flip a coin, only one of those two events can occur. Both events cannot, right? Okay, so these are mutually exclusive. Another example I think I used earlier in the course would be like, you know, one event could be that tomorrow at a specific time it's raining, and then a second event could be that tomorrow at that same specific time it's not raining. Those two events are mutually exclusive. At that particular point in time, it cannot be both raining and not raining. Now, if I had changed that terminology and I said, tomorrow it's raining, and then the second event is that tomorrow it's not raining, that actually could, those two events could actually both occur, right? Because we know typically when it rains, it doesn't rain constantly for an entire day. There are breaks in there in which it's not raining. So anyway. All right, let's look at number two. So a card from a standard deck of cards. So event A is the event that you randomly select a card that's a queen. And then event B is the the event that you randomly select a card that is a spade. So the question here is, you want to ask yourself, could both of these events occur? And the answer is yes, because if you remember, there is a queen of spades, okay? And because that card exists, both of these events could occur, okay? So these are not mutually exclusive. You could select one card and it be both a queen and a spade. Because remember, there are 4 queens, and each queen has its own suit. That be it a heart, a spade, a diamond, a club. All right, what about number 3 here? So event A is randomly selecting a student that is 19 years old, and then event B is randomly selecting a student who is a freshman, okay? So really here you're thinking about, okay, would it be possible for there to exist a 19-year-old freshman? And the answer is yes, okay? In fact, some of you may be 19-year-old freshmen. So because of this, these 2 events are not mutually exclusive. They can both occur, okay, in that there can be a 19-year-old that is also a freshman. All right. Okay, so now what we're going to get into, guys, is actually calculating the probability of some of these unions, okay? So to find the probability that A or B will occur, we add the probabilities. Find the probability of A, and we add it to the probability of B. But then you also have to subtract off the probability that both occur simultaneously. So in other words, you're subtracting off the intersection, okay? So think about that example above when we were talking about the queen of spades. So if I were to just calculate the probability of selecting a queen, that would be 4 out of 52. And if I were to calculate the probability of selecting a spade, that would be 13 out of 52, because, you know, each suit has 13 cards. But what we have done there, guys, in adding those 2 probabilities together is we have counted that one card essentially twice, okay? We count it once for the spades, and we count it again for the queens. So at the end of this, we have to subtract off the probability of selecting just a queen of spades, okay? There's a diagram down here we'll look at here in a minute that'll make it hopefully a little more clear. Okay, so we sum these probabilities. So that's the reason this is called the addition rule. So mathematically, this is how it's defined. Okay, so you have events A and B. So if we want to find the probability of A or B occurring, one of the 2 occurring, then it's going to be the probability of A plus the probability of B minus the probability that they both occur. Now, for mutually exclusive events, this simplifies to just the probability of A plus the probability of B. Because if 2 events are mutually exclusive, guys, we know they both cannot occur together. So this probability right here that they do occur together would always be 0. Okay. Yeah, that's what this says right here. The probability that A and B occur if they're mutually exclusive events would be 0, because by that definition, they can never occur at the same time. All right, so think back to the multiplication rule, okay? So to find A and B, we multiplied. We multiplied the probability of A times the probability of event B occurring given that event A occurred, okay? And if you remember, if those were independent events, meaning one event occurring had no influence on the outcome of a second event, then this simplified to just the probability of A times the probability of B, okay? Now we want to find the probability of A or B, then we add the probabilities and subtract the intersection. So you can sort of remember it this way, I guess. So to sum up, add is going to mean multiply. So if you're trying to find the probability of A and B, you're going to be multiplying probabilities. And then the word or, you're going to add. So the probability of A or B is going to be the probability of A plus the probability of B minus that intersection. And this shows you right here, this is a visual. So let me put this in now, if I were trying to find probability of A or B, okay, we'd say the probability of A plus the probability of B. Now, if that's all I did, so we can represent the probability of A being this circle here, and the probability of B being this circle here. So this little area right here, this intersection, would have gotten counted twice. So really, in finding the probability of A or B, I'm really just trying to find the probability of this whole area, not counting this region twice. Okay, so that's why at the very end we have to subtract off that intersection. Okay, so hopefully that kind of helped you visualize why we have to subtract at the very end. All right, so now let's take a look at some examples. And actually, guys, most of this section is just examples. In fact, that's really all of the conceptual stuff that we cover. All right, so let's look at example 4. We've got a card selected from a standard deck. We want to find the probability that the card is a 3 or is a king. So I can denote it like this: the probability that the card is a 3, or I'll just use a capital K for king. Okay. So using that formula from above, this is going to mean the probability of selecting a 3 plus the probability of selecting a king minus the probability of selecting a 3 and a king. Or in other words, the probability of selecting, well, no, I can't say it that way because these two events are actually going to be mutually exclusive. Okay, I started to say a king and then followed by a suit, but that's not going to be the case. So the probability of selecting a 3, well, there are 4 3s out of a total of 52, plus the probability of selecting a king, there are 4 kings out of 52, okay, minus, and this is where you realize that these two events are mutually exclusive. You cannot select a card that happens to be both a 3 and a king, okay? So the probability of that intersection is going to be 0. And I'm going to put in here that these are mutually exclusive events. Okay, they both cannot occur. All right. So if I do this, this is going to end up giving me 8 over 52, which, what will this simplify to? 2 out of 13, I believe, or 2/13. Okay, so 2 divided by 13, let's round this to 3 decimal places. So this would be 0.154. Okay, roughly. All right, what about number 5 then? A 6-sided die is rolled. Find the probability of rolling a number less than 4 or rolling an odd number. Okay, so I'm going to denote this very similarly. Probability that the number is less than 4 or odd. Okay, so this will be the probability that the number is less than 4 plus the probability that the number ends up being odd minus the intersection, the probability that the number is less than 4 and odd. Okay. So the probability that it's less than 4, so how many numbers on a die, this is a 6-sided die, are less than 4? Well, 3, 2, and 1, so that's 3 of them. So 3 out of 6, plus how many numbers are odd? Well, 1, 3, and 5, so that's 3 as well. Minus the intersection. Okay, so is it possible to roll a number that's less than 4 and odd? And it is. Okay, so these events are not mutually exclusive, so the probability of this intersection is not going to be 0. So you just figure out, well, how many numbers are both odd and less than 4? Well, the numbers 1 and 3. Okay, and that's 2 of them, so 2 out of 6. And when you're doing this, guys, you're going to notice that these denominators are pretty much all going to be the same. So anyway, if I were to compute this, I believe that I'm going to get 4/6, which is the same as 2/3, or 0.667. Okay, so that would be the probability of one of those two things happening. One of those two things happening, or both. All right, number 6. A biology class has 32 students. Of these, 10 are biology majors and 14 students are male. So of the biology majors, 4 of them are male. So we want to find the probability that a randomly selected student is male or a biology major. So probability the student is male, or I'm just going to put biology. Okay. So this would be the probability that the student is male plus the probability that the student is a biology major minus the intersection. So male and biology major. Okay. All right. Well, we're going to use all these numbers that they're giving us. Okay, so our denominators are going to be 32 because there's a total of 32 students in the class. So of those, let's see, 14 of them are male. So the probability that the student is male is going to be 14 out of 32 plus the probability that the student is a biology major. Well, there's 10 of those. So 10 out of 32. And then this other piece of information they give us right here, guys, this is actually the probability of that intersection, because look what it says. Of the biology majors, 4 of them are male. So this means that 4 of those students are both male and biology majors. So that's what we're going to be subtracting off, 4 out of 32. All right, so if you do this, it looks like you would get 20 out of 32, which will simplify to 5 over 8. 5/8, so you divide both those by 4, which as a decimal is going to be 0.625, and this one terminates. Okay, all right, number 7. All of these are kind of the same, guys. It says, of the cans produced by company, 96% do not have a puncture, and then 93% do not have a smashed edge. And 89.3% do not have a puncture and do not have a smashed edge. So find the probability that a randomly selected can does not have a puncture or does not have a mashed edge. Okay, so again, this is a union because of that word or. So the probability, how should I word this? That the can doesn't have a puncture or doesn't have, or actually, let me just say no puncture or no smashed edge. I'm just going to put edge for short, okay? So this would be the probability that a randomly selected can has no puncture, plus the probability that it doesn't have a smashed edge, minus the probability that it doesn't have a puncture, and no smashed edge. Okay. All right, so the probability that the can does not have a puncture, well, it says that 96% don't have a puncture. So you could, I'll put a plus sign, and that should have been an equal sign. You could do percentages, guys, but it's better that you use decimals, okay? Plus, the probability that the can does not have a smashed edge, it says here that 93% do not have a smashed edge. So this is going to end up being 0.93 minus. Now, again, this is the probability that they neither have a puncture nor a smashed edge, okay? So 0.89, whoops, 0.893 as a decimal. Okay, we're going to see what this means. In other words, 89.3% of those cans are going to be perfect. Anyway, let's do this arithmetic. So 0.96 plus 0.93 minus the probability of that intersection, or the probability of both of those events occurring. Okay, 0.997. Well, that's actually close to 1, isn't it? Okay. All right. And also, guys, you know, pay attention to the way the events are defined. In this case, you could say event A is defined to be the event that you select a can that does not have a puncture. So event A could have been the event, you know, that the can has a puncture. It just depends on how the events are defined. Anyway, number 8. So it says a standard deck of cards, we know this, contains 52, and then one card is selected from the deck. So we want to compute the probability of randomly selecting a club or a diamond. Okay, so this is really the same problem that we saw before, the probability of selecting a club or a diamond. Okay, so again, this will be the probability selecting a club plus the probability of selecting a diamond minus the probability that the card you select is both a club and a diamond. Well, why don't I just draw a diamond, okay? I think that's what I've done that before. It's actually easier. Okay, so the probability of selecting a club. Well, a club is a suit, and we know that each suit is comprised of 13 cards. So this would be 13 out of 52 plus probability of selecting a diamond. Well, a diamond is another suit. So there's 13 of those. Minus, now what's the probability that the card is both a club and a diamond? Well, here again, guys, these are two distinct suits, so it's not possible to draw a card that has both of these. Each card only has one suit. So this probability is going to be 0 because these two events are mutually exclusive. Okay, so this is just going to end up being 26 over 52, which is 1/2. And this makes sense because you're talking about all the clubs and all the diamonds, so that would be half of the deck of cards. Okay, part B, compute the probability of randomly selecting a club or a diamond or a heart. Okay? All right, now, at first glance, I would say one like this is beyond the scope of this book, but it's actually not when you realize that these are three events, but they are all mutually exclusive. Okay, now if they were not mutually exclusive, we would not be doing this, because you end up having to subtract off more intersections. Okay, anyway. But since they are mutually exclusive, this is just going to be the probability of drawing a club plus the probability of drawing a diamond plus the probability of drawing a heart. Okay. Now I'm not going to worry about subtracting any intersections because I know whatever those are, they're going to be 0. So this would be 13 out of 52 plus another 13 out of 52 plus the last 13 out of 52, and this is going to be a total of, looks like 39 out of 52, which is the same as 3/4 or 75%. Okay, because there's 3 suits, and we're talking 3 suits out of 4, so that's 75%. All right, what about part C? Compute the probability of randomly selecting a 5 or a club. So the probability of a 5 or a club. Okay, we can do this one same way. And then minus the intersection, the probability of selecting a card that's both a 5 and a club. Well, these events are not mutually exclusive because there is a 5 of clubs in there. Okay. Now the probability of selecting a 5 is going to be 4 out of 52 because there's 4 5s. Probability of selecting a club, well, a club is a suit, so it's 13 of those, minus, and then because there is a 5 of clubs, there is 1 card out of 52 that satisfies both of those events, or is in the realization of both of those events. Okay. All right, so if we do this, I believe it's going to be 16 out of 52, which we can simplify this down to 4/13. Okay, so looks like the 3 decimal places is going to be 0.308. Okay. Guys, we will do this one, but we're not going to do all of it. Let's not do part A, okay? Because we just saw that. We've seen one like this. Which one was it? Yeah, see, the 3 or king, those are mutually exclusive. So here, it's just a club or a 3, so it's the same type of problem. Let's go to part B. Randomly selecting a red suit or a king. So the probability that the card you draw is red, I'm not getting ahead of myself. So the probability that the card you draw is red or is a king. Okay. So this would be the probability that it's red plus the probability that it's a king minus the probability that it's a red king. And these events are not mutually exclusive. So the probability that it's red, well, how many red cards are there? You guys know that half are red and half are black. So that means 26 out of 52 are red plus probability of selecting a king, well, there's 4 of those, so 4 out of 52 minus, and then we know that there is a red, actually, there's there's more than just one red king. There are two. Okay, remember, for each denomination, I guess, there are two red and there are two blacks. There's actually two red kings, 2 out of 52. All right, so this would end up giving us 28 over 52, which I think simplifies to 7 over 13. So this is close, a little over half. So 0.538. All right, and then part C here, randomly selecting a 9 or a face card. We'll go ahead and do this one. So a 9 or, I'm just going to put a face. So this will be the probability of selecting a 9 plus the probability of selecting a face card minus the probability of selecting a card that's a 9 and has a face on it, okay? Well, the probability of selecting a 9 is 4 out of 52, plus the probability of selecting a face card. Well, there's 3 face cards. There's a jack, there's a queen, and there's a king, and there's 4 of each of those. So that's a total of 12. Okay, so 12 out of 52 minus, now we need to figure out how many 9s are face cards. Okay, well, there aren't any. These two events are mutually exclusive again. Okay, you can't have a card that both has a face on it and is also a 9. That's impossible. So anyway, this is going to end up being 16 out of 52, which will be 4 out of 13, which I think is 0.308. I think we had it a second ago. Yeah, we just did ones like that. Okay, I will put in here that those two events are mutually exclusive. Sorry about that, guys. All right, well, let's go on. I think we got a couple examples left. It's just that some of these examples have multi-parts. Okay, so this table shows the number of male and female students enrolled in nursing at the University of Oklahoma Health Sciences Center, okay, for a recent semester. So a student is selected at random. So we want to find the probability of each of these events. The student is male or a nursing major. So the probability of the student is male or nursing major. Okay, so this is going to be equal to the probability that the student is male plus the probability that the student is a nursing major minus, so we'll subtract off that intersection now, the probability that the student is male and a nursing major. Okay. All right, well, the probability that the student is male, well, of the males in this row right here, there's a total of 1,198. Out of the total of all these students is 3,605, plus the probability that the student is a nursing major. Well, the nursing majors are right here in this column, and there's a total of 819, minus the total number of students, which is still 3,605, minus, now we need to figure out how many of those students are both male and nursing majors, or in other words, male nursing majors, okay? Well, the nursing majors are right here, and of those, 94 are male. So there's 94 male nursing majors. All right, okay, so let's do this in our calculator. 819, we'll subtract off. In our numerator, we're going to get 1,923 out of 3,605. And then we'll go ahead and find that decimal. All right, so for 3 decimal places, this would be 0.533. Okay. Part B, the probability that the student is female or not a nursing major. Okay. What do you say? Not a nursing major. All right, so this can be equal to the probability that the student is female. Boy, I tell you, I think the most rigorous part of this section is just actually writing all this notation. Typically what you would do, guys, is you would just say, okay, I'm going to let A equal this event and then B equal this event, and then you would just use A and B. But okay, and then minus this intersection. All right, so the probability that the student is female, well, this row represents the female students, and there are 2,407 out of a total of 3,605, plus the probability that the student is not a nursing major. Well, these are the students that are not nursing majors, see? And there's a total of 2,786. Minus the probability that the student is both female and not a nursing major, okay? So let's look here in this female row, and then of these, there is 1,682 female students that are not nursing majors. So 1,682 out of that same total. And we're going to need to use our calculator again here. Okay, so 3,511 out of 3,605. Let me also point out something, guys. If you were to ever get a numerator that's bigger than this denominator, then you've made a mistake somewhere, okay? And what I'm noticing in this one is that this is actually going to be very close to 1. So if you were to randomly select a student at this school, you would be close to certain that that student would either be female or not a nursing major. Okay. Anyway, let's see what this actual decimal is. All right, so to 3 decimal places, it'll be 0.974. All right, and then part C, probability that the student is not female or is a nursing major. This one's really just kind of the reverse of this previous one. Okay. Well, yeah, I think maybe we'll just skip it, guys, because it's really just the same as this one. And we've got a bunch of examples in this section, probably more examples than you'll actually have homework questions. All right, so let's do one last one. Number 11, okay? All right, so what we've got here, the percent of college students' marijuana use for a sample of 95,761 students is shown in this price chart. I should say pie, obviously. Sounds like whoever did this may have been, could have been smoking marijuana. But anyway, so we want to find the probability of each of these events, okay? All right, so let's look at this pie chart. So it says marijuana use in the last 30 days. So of these students that were sampled, 60.3% said they never used marijuana within the last 30 days. And then 21% said they used marijuana but not in the last 30 days. And then 12% said they used within the last 1 to 9 days. And then 4% said they used within the last 10 to 29 days. And then this last one, 2.7% used on all 30 days. Okay. So part A, we want to figure out what's the probability of randomly selecting a student who never used marijuana. Well, you can see here it's going to be this region of the pie. And so that would be, well, you could just write 60.3%. Or if you want to do a decimal, this would be 0.603. Okay. All right, part B, randomly selecting a student who used marijuana. Well, if you used marijuana, it doesn't matter the time period, okay? You used it, so that would actually be all of these smaller slices of the pie, okay? So we need to add all of these up. So really, in the context of this section, guys, using the addition rule, what you're doing here is you're sort of saying, oh, okay, well, what's the probability that of this or this or this or this? And because the way they have it laid out here, all these events are like mutually exclusive. See, some 12% used within the last 1 to 29 days, 4% used within the last 10 to 29 days. So see, these time periods don't overlap. So you're really just adding up all these individual probabilities. So anyway, this one is going to be the 21% plus the 12% plus 4%, okay, used within this time period, 10 to 29 days, and then 2.7% used every day. Okay, so I'm just going to add all these up. Let's see, would this be 33, 37, 39.7? I didn't make a mistake. So that would be the probability that a randomly selected student did use marijuana, okay, not specifying within a certain interval of time. All right, part C, randomly selecting a student who used marijuana between 1 and 29, oh wait, I'm reading this wrong, who used marijuana between 1 and 29 of the last 30 days. Okay, so what you've got to do here is you're going to be adding up this probability, the probability that a student used it anywhere between 1 and 9 days ago, plus this probability that the student used it anywhere from 10 to 29 days ago. Okay, and then we're not worried about this one. All right, so it's going to be 12% plus 4%. And this is going to be a total of 16%, or 0.16. Okay. All right, part D. Randomly selecting a student who used marijuana on at least one of the last 30 days. All right, so if you used it at least one of the last 30 days, then that would be this wedge of the pie plus this wedge of the pie plus this wedge of the pie. Okay, so that's going to end up being 12% plus 4% plus 2.7%. So you're really just including that very last small slice of the pie there. So this is going to end up being 18.7%, or 0.87. Okay. So like I said, you're sort of treating these events as though they're mutually exclusive. That's how we're able to add all these up without subtracting any intersections. Okay. And we were worried about there being overlap, guys. Then this problem could become much more complex. But we're just looking at each of these events as being mutually exclusive. Okay. So anyway. Right, guys, well, we got one more section in Chapter 3, that's 3.4, and I'll see you in that section.